Okay, so now that we've got the circuit figured out and how that relates back to the biology, let's talk math.
Yeah. Go for it.
Okay, so where do we start?
Well, maybe we should focus on the ion channels and see if we can learn something interesting. Just focus on that right-hand branch. See if we can learn something interesting about the relationship between current and conductance or resistance and voltage.
Okay,
Let's try that.
so we'll start from here, as you were saying.
So what's the total voltage across the membrane?
Voltage across the membrane would be, like, due to this
Yeah, due to this. Now,
branch?
before we go and do that, actually, let's look at what's the relationship between current and voltage and resistance. I don't think we worked that out yet, so let's do that first.
Okay, so we've got voltage.
Which is a potential to do work on, say, ions.
Mm-hmm.
Now, the larger the voltage across an ion channel, what will that do to the current?
Wouldn't that make the current higher?
Exactly. So you could say that V is proportional to the current, right? Now, if it's very, very high resistance, how much current do you get?
Low current.
And if it's very low resistance, you get?
High current.
So let's put in a constant of proportionality, and let's just call it R. Oh, V equals IR.
And that's Ohm's law.
Let's write that down.
Okay.
And let me just say this again. If resistance is very, very high for a given voltage, how much current do you get?
If resistance is high for a given voltage, then you have a low current.
Exactly. And if the resistance is low?
Then you have a high current.
Exactly. The way you can think about it in terms of this is if this is like a pipe that lets things flow through it.
Mm-hmm.
If it's very narrow, it has a very high resistance, and it's hard to flow through it.
So you're not going to get much flow or
Exactly.
current.
And if it's very broad, then you can have a lot of things flowing through it.
Okay.
And so for the same voltage, you'll get a much higher current flowing through it.
Okay.
That's V equals IR. Now, we also had a way of writing this in terms of conductance. How should we do that?
So if, all right, resistance equals 1 over conductance.
Right.
That's what we had determined before.
That's right.
So if you subbed that in, you would get V equals I over G.
Right.
Which would be more simply written as Vg equals I.
Right. So that's another form of Ohm's law in terms of conductances. Okay? Excellent. All right. Now, okay, so if we now look at the right-hand side here, we see that there are two potentials. There's a membrane voltage across the whole membrane. We could call it Vm, and we could put a little line on the top and the bottom to indicate where it goes. That's right, Vm goes across this whole thing. And now it's composed of two pieces, right? It's the flow of current through here, through the resistance by this law, and then it's the battery.
Okay.
So let's write down those two components. We can say the voltage across the membrane, Vm, is equal to the sum of what?
Well, first let's put this in terms of V.
Okay.
Again.
Good.
Actually, that's...
Yeah, that's right. I over G.
So Vm equals I of an ion.
That's right.
Over G of that ion.
Right. Plus...
And then we have to add this battery bit.
Right, which is also going to be E sub...
This is E sub ion.
Excellent. And now, okay, so this is perfectly good, but we might want to solve for this in terms of current.
Okay.
Let's do that.
That's because later in this course we'll be injecting current into cells,
That's right. We want to see how the current, or we might want to see how the current is affected by the voltage across the membrane and its conductance. So let's solve for the current.
So this means that I ion over G ion would equal, this is Vm minus E ion.
Right.
Which then turns into I ion equals G ion times Vm minus E.
And very important equation. And now let's say it in words, which will help people remember it. It says that the current is equal to
the conductance times sort of this
difference. Now this is given its own name. What's the name that we give to this?
This is the driving force.
Let's write that down because that's a new thing that we haven't said before. And now let's think about it. If the membrane is at the Nernst potential of the ion, what happens to the driving force? What does it become?
So if these are equal,
that's right.
Then the driving force should be 0.
And how much current will flow if the driving force is 0?
None.
Right.
Because you don't have this sort of push and pull between the membrane voltage and the Nernst potential.
That's right. Good. And what happens if you shut all the holes for that particular ion? What happens to the conductance? What value does it have?
Conductance would be 0
because,
which is the same thing as saying it's very, very, very not easy to get through the membrane.
It's like an infinite resistance gives you a 0 conductance, and how much current do you get through?
0.
Very good.
So this is going to be really important.
Very important. We're going to see this over and over again. This is really worth remembering.
Okay.
And now we have the last thing we'd like to do, which is to talk about the other branch and see what we can say about it.
Okay. I'm going to erase what we've got, so everyone write it down. I'll rewrite it over here. Or no, we'll just write things over here.
Okay, yeah, just leave that equation over there and erase that. That's good. Okay. So now what we want to do is to look at the relationships between the voltage and the capacitance and charges and current.
Okay.
So what we saw was the more charges you have on a capacitor, the more that land on the membrane, what happens to the voltage? You have charge separation, and what does that do to voltage?
Well, let's start by saying, so if this is just sort of at its stable state, where we've got as many negative charges as we can here and as many positive charges as we can here,
that's right,
then nothing's happening.
That's
right. Right? It's this change of having
things
new
land
positive
or go
ones
exactly. So
move that way.
So let's call all that charge that's stored on the capacitor, let's call it Q.
Okay.
What's the relationship between Q and V, the voltage across the membrane?
They're proportional.
That's right. So let's just write down proportional. Now, again, if we make the plates larger, we can store more charge.
Okay, that's like looking at a larger patch of membrane?
That's right. Or if you had, that's right, a larger patch of membrane or a cell that had a larger surface area, it can have a larger capacitance.
Okay.
Now, if you separate the plates, what do you think happens to the ability to repel charges through the membrane?
It would lessen.
That's right, which means that you're going to reduce the capacitance. So all of these things actually make perfect sense.
Mm-hmm.
Now, we had this clever trick. We changed V proportional to I into the V equals IR.
Okay.
Let's do the same here. Let's have a proportionality constant, which we talked about already, call it the capacitance. Mm-hmm. And now we have Q equals CV. That's the fundamental capacitor equation.
Mm-hmm. Where C is capacitance.
That's right. Now we talked about the fact, and that's stable, and it could stay like that forever.
Mm-hmm.
But if we're interested in currents, we're interested in changes of charges with time.
Okay.
So let's take this step at a time. Let's imagine we changed a little bit of the charge. We could represent that as delta Q. And from this equation, that's same as saying C times
delta V.
Because the change in charge will cause a change in voltage.
Mm-hmm.
Now let's say we did that per unit time delta T. Okay?
Okay.
So we're looking at a rate. So we would divide both sides.
I'm just going to divide them right
That's
here.
right. We're trying to do the change of charge per, say, some unit like per second.
Mm-hmm.
And now we have delta Q delta T is equal to C times delta V delta T. In other words, the change in charge with time is equal to C times the change in voltage with time.
Okay.
Good. Now, delta Q delta T, what is change of charge in time? What is that equal to?
That's current.
Yes, that is just current, I. And now, if we do that for very tiny time increments, we could rewrite that as just I is equal to C dV dt, which is just the instantaneous rate of change of the voltage with time.
Okay.
And that's the capacitor equation.
Cool.
So let's put a, and that
big
now,
important box around.
That's another important box around that. So now we have the resistor equation and the capacitor equation. And that helps us understand how the membrane will change when you add or remove charges, because first they'll land on the membrane and do stuff to the capacitor, and only after they're finished doing most of that will they start running through the ion channels, and then this is going to start to dominate. So those are the two things you have to keep in mind. All right?
Yep, that makes sense. So these are our two big equations.
And if we're going to just understand the passive membrane, these equations are going to really help us.
Cool.